Let's say that we have a fence of length L. So we have fence of length L. Let's represent it like this. And we want to use this fence to enclose a rectangular area, and we want this area to be the maximum possible. So we have a limited amount of fence, a limited length for the perimeter, and we want to maximize the area of the rectangle. How can we do this? Is there a general, way to go, or maybe does it change depending on the length? We'll see. So let's just draw a rectangle and try to figure out some steps that we can take to tackle this problem. So this is going to be the rectangle that we're talking about. Let's say that one side of this rectangle has length A, let's say. And what about the other side then? We know that the perimeter of the rectangle is going to give L. I mean, that's the condition that we're doing this problem. So that means this is A as well, and let's say that this is B, but we will shortly express B in terms of A and L. We see that 2B plus 2A equals L, so A plus B equals L over 2, which means that B is equal to L over 2 minus A. So we can write then L over 2 minus A for this. Okay? And now, what is the area? The area, it is going to be a function of A. And of course, we can write it as a function of B as well, but since we expressed B in terms of A, it is more convenient to find the area in terms of A. So what is the area of a rectangle? You just multiply the two sides that are perpendicular to each other. So then the area as a function of A is L over 2 minus A times A. And if we write this, if we distribute the parentheses, that is A L over 2 minus A squared. Cool. Now, we want this to be a maximum, and if we are doing a maximization problem, we are probably going to use an integral, because they help us to find the maxima and minima of a function. So let's take the derivative of area with respect to little a. We are taking the derivative of the area with respect to the length of this side. This is the parameter. This is the variable that we are using to take the integral. I mean the derivative, not the integral. Sorry. Okay. So how do we integrate this? This is fairly simple. If you know derivative, basically, if you know derivatives, this is fairly simple. This is going to be L over 2 minus 2A. And we want to set this equal to 0 so that we can find an extremum point for the function, which means a minima or a maxima. And these are local minima and maxima. So this is equal to 0. Then 2A is equal to L over 2, which means then that A is equal to L over 4. And of course, we need to decide whether or not this is a maximum or a minimum point. And for that, we look at the second derivative. What is the second derivative? That is, well, we just take the derivative of this part without equalizing it to 0. So this is the part that we're taking the derivative of. And that just gives you negative 2, which is less than 0. And since the second derivative is less than 0, this means that the function is concave down. It is something like this. And it is second degree, so it is a parabola that is pointing downwards. Alright? And it is in fact even going to touch the origin, because I mean, if we were to draw it on a coordinate system, let me do it. So if this is A and this is the area, capital A, if we plug in 0 for the little a, we get that. So here, if we plug in 0, we get 0. So this is touching the origin, which means that the origin is one of the roots of this parabola, and the other root, well, we just found it, didn't we? That root is here, and it turns out it is L over 4. Okay, so it needs to be L over 4. But if the value of A is L over 4, quarter of the length of the total fence we have, well then we should realize something. We should realize that what we need to construct is a, drum roll please, it is a, yes, you guessed it right, it is a square. It is a square because B is L over 2 minus A, so L over 4, it is L over 4 then. A and B are the same, so we should construct a square for the maximum area for a length of L over 4. For a length of L. So each side is going to be L over 4 in this square. This is 90 degrees. And this was also 90 degrees in the rectangle. And I mean, you need to notice something. You probably noticed this, but I am not saying that if we have a length, if we have, let's say that we want to enclose an area, and that area can be in any shape, and the only condition is that the circumference, the perimeter of that area is L. I am not saying that in that condition the most efficient, the shape that yields the greatest area is a square. I am not saying that, because in fact we can just check this. If we were to construct a circle, let's say the circumference is L, so 2 pi r equals L, then r is equal to L over 2 pi. Okay. And we know that the area is then, well, area is going to be pi r squared, right? So it is pi, what is r? It is L squared over 4 pi squared. Pi simplifies, so we have L squared over 4 pi. And what is the area for the square? It is L over 4 times L over 4, so L squared over 16. And it's 16 is 4 times 4. And here in the denominator we have 4 pi, which is less than 16. So we are dividing L squared by a number that is smaller than 16, which means that this would give a greater result than the area of the square. So in fact, if we were to construct a circle, the area would be greater than that of a square, and in fact than that of any rectangle, because square is the rectangle that gives the maximum possible area for a specified length. Okay, I just wanted to point this out. Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section, and I hope to see you in another video. Until then, take care.